Right. So Emma has very kindly, Emma is a principal engineer for QODA, and Emma works in the sustainability team in their Bristol office, and she has very kindly agreed to offer a presentation on a beginner's guide to thermal bridging. Now, this follows a publication you actually produced, Emma, which I managed to have a look at and found very, very interesting, and thought it was valuable to disseminate it to building engineers who are here today.
Well, thank you.
In their 80s,
Oh,
as in 80 in total.
Oh,
So without further ado, could I ask Emma to take the stand and to offer your presentation? Thank you.
Super. Yeah. Thank you, Michael. Yeah. Hello, everyone. Thank you for joining us. Yes, I'm Emma Mathias-Jones, Principal Engineer for CODA in Bristol. So I'm a certified passive house designer and a kind of specialise in net zero carbon strategies, building physics, fabric advice, and kind of building performance modelling. So, and CODA as a whole work on, mechanical, electrical, and sustainability. Those are the kind of core areas. And I'm just going to talk about today what are thermal bridges and why are they important. It might be easier to do questions at the end if you have any, but just maybe put them in the chat or something and we'll try and get to them. So I thought today beginner's guide. I thought we could talk today why we need to think about thermal bridges, the types of thermal bridges, how to identify them, some conventions, and then the new Part L requirements. So you've got a kind of hopefully a good overview, but not too overwhelming. So for a bit of background, we'll start with the building energy demands, which probably you're kind of familiar with. So this is a graph showing the energy demands of a building. On the left-hand side, at the bottom, we've got the fabric heat losses from like the planar elements. So you've got your windows, doors, roof, floor, walls, those type of things. Then we've got thermal bridges, which we'll come to later. And then we've got our ventilation and our infiltration heat losses. So infiltration is like, unintended leakage through the building envelope, and your ventilation is for, your ventilation system, which you need for occupant thermal comfort. The kind of planar elements at the bottom, the walls, windows, floors and things, they're measured in a U value. So the lower the U value, the lower the heat losses will be. So for high performance buildings, you can expect U values for like walls and roofs and stuff in the region of 0.1 watts per meter squared Kelvin. And for new dwellings to Part L, that's in the region of 0.26 watts per meter squared Kelvin. So just to give you a rough guide. And then as approximate, like rough rule of thumb, your heat losses from your windows are about 10 times worse than your walls. So that's why we want to kind of minimize those as much as possible. And then on the right-hand side of the graph, we've got our solar gains, and we've also got internal gains, which are things like, lighting, people, equipment. So these free gains are normally a lot lower than your heat losses. So the difference, we have space heating makes up the difference. And to put that into a little bit of more context, for passive house, that figure needs to be below 15 kilowatt hours per meter squared per year. For AECB, that needs to be below 40. And building regs uses a slightly different metric, but roughly, they're often significantly higher. So if we were looking to lower that heating demand, we could look for improving the U values of. So that's fairly straightforward. You add more insulation. We could make the building more airtight, so reduce that infiltration, and we could also look to use a system like a mechanical ventilation with heat recovery system or something like that. But then, as we reduce the U values, the thermal bridging gets even more important. So that's something that we also need to address. And so this is the bit that's becoming ever more important. So Mark Elton has this great image to help describe how, so as you reduce your U values, which is like the grip tightness, your thermal bridges become more important, and those are the gaps. I think it's quite a good way of summing it up. And as you get tighter, it gets more and more critical. Yeah, so we know where it sits. So we know where thermal bridging sits in terms of energy demand, but there's lots of different types. So they're typically kind of lines or points of the building which have worse thermal performance than the areas around it. And so BRE Information Paper 1-06 says thermal bridges can occur at any junction between building elements or where the structure changes. And these are typically split into two main groups. So repeating and non-repeating. So where the building structure changes, like there's often a repeating thermal bridge, and any junctions kind of between building elements is typically called a non-repeating thermal bridge. Just to make it a little bit more complicated though. So yeah, repeating thermal bridges are things like water joints, wall ties, ceiling joists, joists in cold pitch roofs, essentially building, thermal bridges that are kind of regular and repeating across a building element. And those we include in our U value. Those are hopefully fairly straightforward. But then there are the non-repeating thermal bridges, which are, discontinuities in the building envelope. And those could be split down a bit further. And so, you've got non-repeating linear thermal bridges, which are often kind of at junctions. So things like your perimeter ground floor, your eaves, your like around windows. And then you've got non-repeating point thermal bridges, which are more things like SVPs, flues, isolated steel beams, or fixings, or like or the junction of three planar elements. So those are the kind of core types, and both of those non-repeating, so non-repeating linear and non-repeating point, they need to be accounted for separately to your U values. So just to summarize that a little bit. So on the far left, we've got our element heat loss. So that's your kind of walls, floor, roof. That's measured in your U value for a given element, and that's on a kind of per meter square or area basis. And those include repeating thermal bridges. Then in the middle, we've got our linear thermal bridges, and those are described as a psi value, and that's measured in a watts per meter Kelvin, or like a length. And then we've got our non-repeating point thermal bridges, and those are called chi values, and those are measured in like a point or a watts per Kelvin basis. And then together, those three, the three different bits, make up your total building fabric heat loss. But how do we spot them? I thought we could just run through an example project. Obviously, it's 3D, which isn't what you always get. You mostly get plan sections, elevations, but I thought it might be kind of an easier way to describe it. So just something to keep in mind is that insulation zone. That's kind of what we're worried about, where that changes or where there are things causing discontinuities in that. So that's something we want to keep in mind. And then sorry, back to this one. So what I find useful is if I'm looking at a project and trying to identify the thermal bridges, I'll list out all of the ones that there kind of could be, even if I know that they might be able to be like designed out or like reduced, just so I can keep an eye on them as the project progresses and so they don't become a problem. And also as the project progresses, it's really good just to keep an eye, just in case there's any new ones that have kind of snuck in. So I'm going to be following the SAP kind of references, and there's some really good guides similar to this that are available where they kind of show you, highlight where those thermal bridges might occur and the references. So that these are kind of the conventions that I'm going to be following in the example. So we start off, window lintels. Those are your window installation thermal bridges. Window sills, your jambs, door lintel sills and jambs as well, similar to windows. Your ground floor, your normal ground floor junction. Your wall-to-wall corners, your normal corners, and then inverted corners. Then we've got eaves. So I've assumed there's insulation at ceiling level for this building. So you've got your eaves, thermal bridges, your gables, your intermediate floor, so where your internal floor joins your walls. And then you're going to have others such as your internal walls to your floor junction, Ones like your loft hatch, which are a bit sneaky, often get forgotten about, and then some point thermal bridges like your soil vent pipes, your MVHR intake and exhaust, your intake and exhaust ones. But yeah, the thermal bridges that we just talked about there for your windows and your doors are your window installation thermal bridges. So windows, obviously, you've got glass and frames, so they're a little bit more complicated. So if we just delve into those a bit more, this is a plan view of a window. So we've got our wall U value, which we've we've accounted for separately, but we've got our U value of our frame, U value of our glass, and then we've also got the U value, the psi value of the thermal bridge spacer bar, which is the junction between your glass and your frame. And then we've got the same thing between the frame and the wall. So that's your psi, your thermal bridge of your window installation. And yeah, those kind of together are the main elements of windows that we need to think about. And your U value of your frame, your glass, and your psi spacer bar, those are all included within your U value of your window. So the bit that we were talking about earlier is your psi window installation or your thermal bridge. So that's like the E4 of the window jamb we just went through. So that's just to help clarify there. And then in your window U value, you'd also include things like mullions and transoms in that. And then how do we model? How do we model them? So we know where they are, but how do we model them? Your linear thermal bridges are typically modeled in 2D, and your point thermal bridges are in 3D. This will vary depending on the kind of complexity and conductivities, but that's just a rough kind of guide. And we use a whole bunch of, there's loads of different softwares available. So Flixo, Therm, Heat 2D, 3D, Xitherm, Comsol, and things. So this is just an example from Flixo. These images are from Emma Walshall's book, Understanding Passive House, which is really handy because they've got loads of examples of junctions, your thermal bridge calculation and your psi value for that junction. So it's really useful for early stage. So ideas for how to improve your junctions, but also kind of a rough psi value of what you can expect, because psi values are quite tricky to predict. So it's nice to kind of find something similar, just so you know roughly what you might be able to achieve. But there's loads of information. She's got loads of different books on lofts and like residential, commercial basements and stuff. So there's loads of examples there if you need. There's also so there's lots of. She's also got the Flixo files as well, which is handy if you need to change something slightly. So how are they modelled? So we often use the BRE 497 conventions, and so those will model the kind of the junction, the heat loss for a junction as a whole, and then from that you kind of subtract your U values, and then you're left with your psi value. So there's different, as you can see here, this is an example of an intermediate floor junction. So in the middle, you've got the kind of conventions, your measuring conventions, and on the right is the kind of actual model. And then you can see your psi value for that junction is 0.202, which isn't great. Here's another example of some windows. So it takes you through this BR497, takes you through any conventions that you'll need for any of the calcs, which is really handy. So these are some window that you kind of expect these sort of outputs. So these are all 2D junctions in Flixo, and the results of your psi value. The zero carbon hub also has some really good examples of how to improve your details. So you can see here that adding an internal leaf of low density blocks just improves your psi value from 0.17 to 0.06. So that's really good. I mean, the insulation in the wall doesn't look particularly thick, so the psi value might actually be a little bit worse if you increase that insulation, but this gives you a good gauge. And then it also talks about problems to avoid, which is handy. Also, another resource if you need kind of estimates for thermal bridges at early stage projects are on the Passive House component database. They've got for lots of timber frame systems, they've got lots of psi value calculations. So it's a good resource there. But if we look at, this is a window sill from the Zero Carbon Hub. It just says, ideas on, improving that junction, the sill junction. And if we can see that there's not much insulation here, and the window's kind of not quite in line with the insulation in that base case. And the improved detail, there's a bit more joined up. You've got the glass and the frame, and it sort of all joins up with the insulation a little bit better. You see, in contrast to this detail where the window's, central to the insulation zone, it's a much more, you've got really good U value there and a really low thermal bridge of 0.038. So that's, it's really good detail there. They go through loads of different ones. So why are we concerned now? Like, if they've always been a thing, why are we kind of so worried? This is an uninsulated windowsill junction. So on the far left image, you can see where the cooler areas are in that darker blue and the warmer areas in that kind of red section. So you can see the whole wall is fairly cool. And then you can see, the heat flux, or like the rate of the heat loss. And then you've got your kind of thermal transmittance due to U value is that light orange, which is quite chunky. And then your transmittance due to thermal bridge is that darker orange. And that's, not significant compared to the, the U value is the main element there. But if we add some external wall insulation to this, what happens is your U value decreases, but the effect of that thermal bridge is almost puts you at the same point as an uninsulated windowsill junction, which it's actually, we've really got to consider that junction if that's where quite a lot of the heat loss is going to occur. So this shows how, if we think about not just adding external wall insulation, but improving that thermal bridge, how we can reduce those reduce the thermal transmittance significantly. So here what they've done is they've moved the window into the insulation zone, and they've used like a thermal break product. So something maybe like compact foam or Patel's Almacert, just kind of to support the window in that zone. And that's, you can see how much of a difference that makes. Some real life examples. So on the far left, you can see there's a course of thermoblock, which is at the foot of the internal partition. And that's to help reduce that thermal bridge there. And you've also got your SVP, so that would be a point thermal bridge there. The next slide, we've got a steel penetrating the beam and block floor, and it would be a point thermal bridge. And to help mitigate that, we've got insulation wrapped around it. And then here we've also got point thermal bridges where the balustrade sanctions connect to the warm steel roof, and there's a Farrett pad. It's a bit hard to see, but there's like a Farrett pad structural thermal break in there. And then finally we've got the same point thermal bridges from those steel penetrating the beam and block floor, and those have been improved with insulation wrapping around, which is good. I mean, and there's loads of different products available. Just a few examples here. The wall ties. Balcony connectors, foam glass perimeter insulation, things like that. So there's lots available now, which is really handy. Another thing to keep in mind while you're doing thermal bridges is your surface temperature condensation risk. Now this is different to interstitial condensation, but so we're just looking at surface temperature. So when we're doing a Flixo calc, as you can see here that's circled, we can also use slightly different boundary conditions, but we can figure out what the lowest temperature is of that junction. So in this case, 19.3, and that results in an FRSI of 0.976. So that is the kind of, because there's extra heat loss at those junctions, it results in cold spots, and those cold spots could result in condensation. So condensation, then potentially mold, which we want to avoid. So this FRSI factor is the difference between the internal temperature minus the external temperature divided by the average temperature difference between the inside and the outside. And what we want to try and aim for is for dwellings above 0.75 for that FRSI. So what we've got here is great. It's near towards 1. So there's kind of a low risk of surface temperature condensation, which is great. yeah, some surface resistances just for reference. And this is yet another example. So in house A, on the left-hand side, we're adding external wall insulation. So you can see how that internal point is down at 16.5. That has a knock-on effect. Oh, maybe. And then, yeah, then an external wall insulation option and an internal wall insulation. So you can see how the FRSI in house A is looking pretty good, but you can see the knock-on effect on house B. The FRSI has got quite a lot lower. So that's, yeah, something to keep in mind. And then we've got, yeah, some of the conventions to keep in mind when you're looking at these. So if we're looking at SAP or Part L, although the thermal bridge model for both of these is the same, the way where we take the measurements from is a bit different. So for SAP and Part L, we're looking at those internal measurements, and so we get a psi internal, and those are the green lines. And then for passive house or AECB, you're using external lines, which is the red ones, and that gives you a psi external. So those, because of where the measurements are taken from, that will result in different psi values. So just be really cautious when you do get a kind of a thermal bridge calculation given to you, you know which one it's for, because they will be different. The SAP Part L is often a bit of an underestimate. The passive house is a bit of an overestimate. Sometimes it can be kind of, yeah, much less or even a negative just because of the way the geometry works. Typically, you might hear sometimes like junctions are thermally bridge free, and that roughly means that you've got a psi value of less than 0.01 watts per meter Kelvin. But there'll always be a value associated with that. But yeah, the lower the better. And point thermal bridges typically are a lot lower than your kind of linear thermal bridges, but they're becoming increasingly more like of a concern, particularly, and you should always include them if you've got kind of like highly conductive elements through your insulation layer. So for example, here it's got a steel girder, and they're saying, you know, you've got to calculate those chi values. If you're looking at steel, that's probably a 3D thermal bridge that you'd need to do to calculate the heat loss for that, because something to keep in mind. And then, yeah, where this sits in terms of the new Part L. So for dwellings, these are the kind of the requirements, and what that essentially means is there are 3 sources of information where you could get a psi value from. Essentially, it's just actually calculating the junction. And then, yeah, this is a bit, yeah, this summary hopefully is a little bit easier to digest. So if you're not calculating the thermal bridges, your actual model will use a Y value of 0.2. So a Y value is kind of like it's like taking the sum of all of your psi values for your chi values for that dwelling, and you divide them by the external area, and it kind of is it's kind of like a thermal bridging factor. So as you can see, yeah, your actual model will use 0.2 and your notional will use 0.05. So there's a big difference. So it's kind of worth calculating. If you are calculating them, you've got your length, you have to calculate each psi value separately, and there's 3 possible data sources for that. And those will be compared to something, a thermal bridge of the same length, but the psi values that are found in table SAP 10.2 table R2. So, and those will probably be roughly in line with that Y value of 0.05. So for residential buildings, it makes a lot of sense to calculate them if you can, because otherwise it's going to be, yeah, you're going to be kind of having to make quite a lot of improvements elsewhere, like, I don't know, more PV or better infiltration rate or something like that. So it's often sometimes maybe a bit more cost effective to calculate your thermal bridges, or some, if not all. And then we've got, buildings other than dwellings. It's fairly similar. So if you're not calculating your thermal bridges, your actual model will assume a 25% uplift on the U value, and your notional will assume a 10% uplift. But there's a little bit more scope in terms of you can use some kind of default psi values, but they add on a bit of a buffer. So you can use figures from BRE information paper 1-06, but you have to either increase them by 0.04 or 50%, whichever one's the greater. So Still not great, but there's kind of a bit of a little bit more flex there but you can also calculate them if you want to. And those will be compared to kind of junctions of the similar length, but the values found in the NCN modeling guide. And just to explain that uplift a little bit more. So you would get that psi value of 0.16, but you'd increase it by either 0.04 or 50%, whichever one's the greater. So in this case, it would be that 0.24. So it would still be quite high. So you might want to actually get the actual psi value of that junction anyway. And yeah, that's what we're being compared against. So yeah, this is just a rough summary. So at the top, we've got our measured psi values from according to BR 497. These are just some windows that I've chosen. Looking at those against our approved old SAP approved details, your lintels doing fine, your sills doing fine, your jams are a little bit worse. But then compare that to the new dwelling, you can see how much it's sort of stepped up. Your lintels are now being compared to dwellings 0.05, so that's quite a lot lower. Your sills 0.05, so that's okay. But your jams, and then non-dwelling, similar case. It's getting a lot harder to meet those criteria. So we've to effectively mitigate heat losses and like reduce that risk of surface temperature condensation, we know how to identify them, thermal bridges, ideas for where to improve them, calculate them, and just to check that condensation risk. So hopefully, and some more watch points here. Hopefully now, it's got a better gauge of why it's important not just to look at the U values, but like those thermal bridges in particular for retrofits. Thermal bridges, tricky to predict. Then the Part L SAP defaults are pretty poor, so it might be more cost effective to calculate them rather than leaving them as defaults. And then you've got to just make sure if you do get a psi out of thermal bridge calc, you know if it's an internal or an external one, because they will be different. You can use your thermal bridge model to calculate the surface temperature condensation risk, but just keep in mind there's different boundary conditions there. So hopefully now you know why we need to think about thermal bridges, the types of thermal bridges, how to look out for them, conventions, and a little bit on the Part L requirements. That's
How do we ask questions?
I'm not sure. Maybe in the chat.
If we could put the questions on the chat. In the meantime, your presentation, Emma, is that something that could be shared with the members on this call if you were to forward it to Rosemary at HQ?
Yeah, I'm sure that's fine. Yeah.
So if you could forward your presentation to Rosemary at HQ, we can then send that out to everyone who's registered to attend.
Yeah, no problem.
We've got a couple of calls here, which would be, wouldn't an external PSI value be a negative value?
It can be. It just depends on the geometry. So sometimes it is, but not always.
Another question's come through is, does psi value only deal with non-repeating thermal bridges?
Your psi value, yes. So your repeating thermal bridges will be typically included in your U value calc. You could include your repeating thermal bridges as a psi value, but generally that's it's not often the case. But typically your non-repeating linear thermal bridges are you want to include separately.
Okay. A question from myself then. With the new approved document L that's come out and it being implemented, there is a greater emphasis on thermal bridging and the need for photographic evidence to be undertaken. Now, you've made mention of the psi value and the other internals and external value. How would a practicing building control practitioner know that a full evaluation on the thermal bridging has taken place to show full compliance with approved document L?
So you generally have those like Flixo results at design stage, and then photos from on site, maybe delivery notes as well, of any particular special like thermal break products that you have.
And who would dictate what those thermal break products should be, and what photographs should be taken? And the next question is, we're not all David. Well, not us, but the person who's taking the photos may not be a David Bailey specialist. How do we know that we're going to get the right photos in the areas that you, as the consultants, have highlighted within your report? Would you be taking an active role on site, ensuring that the coordination between your report and the contractor's submission of information meets the requirements?
So yeah, it's a tricky. I think things like delivery notes, and if they're key junctions, it would be kind of someone coming on site to kind of make sure they're the right ones going in.
Would you
Often,
highlight that though in your report to, for example, building control or the clients, to say these are critical locations that should? Is that the sort of thing those in the industry should be asking the pertinent questions of the main contractor or of the consulting engineer?
I think there would be potentially something for the main contractor to do. I mean, for Passive House, it's a bit different. There's a bit more kind of quality assurance there. So you'd need to have a bit more, you'd need those photos. Potentially, you'd have to witness it on site, some key ones, and get those delivery notes. Building regs, I'm not 100% sure. But in terms of who's deciding on those thermal break products, that would be something kind of, say, like we would work with an architect to kind of, ideally reduce the thermal bridge as much as possible first. You wouldn't need those products. So if you can, reduce the need for them as much as possible. And then there's lots of different products for the same junction or same. So it would be kind of testing them out, which one gave you that best, the best site value.
So in essence, then architects should be working with you to design out potential cold bridges and thermal bridges using proprietary systems that are on the market, rather than creating one through construction designs.
Yeah, you just want to kind of that continuity of insulation. Like, if say you've got a steel structure, ideally you rather than putting insulation between it, you want to put insulation either completely within it or outside of it. So then you're kind of eliminating any steel going through your insulation layer. So that's kind of the best way. But if you can't avoid that, then there are products that you could use.
Okay, right. We've got some more questions now. Does BRE follow the new Part L?
So the new Part L requires, I think BR 497. I can't remember the number off the top of my head, but that follows that guide. That requires that guidance to be followed, and you've got all the conventions in there. So.
Okay, so people could reference the BRE guidance that you mentioned in your presentation as a means of ensuring compliance with that particular detail.
Yes, yeah, that's in Part L.
Okay, it might be the same question, but another one that's come up is, where can you find the thermal bridge calculations?
Where can you find them?
Yeah.
So there's a few. Estimating them is really hard. So you either have to calculate them, or those couple of example sources. So that Understanding Architecture book, she's got loads of detailed examples, but they'll be similar. So you have your thermal bridge calculation has to be exactly the same as your detail that you're drawing. If it's a little bit, any changes in the thickness of your insulation will change your psi value. But at early stage, it's good to get a rough gist. So Understanding Architecture book is handy reference point. Your Zero Carbon Hub is a good reference point. There's also, Tom Dollard's book, Understanding Architecture, has got a few good guidance there. And then those, if you're looking at Passive House, the component database has some kind of psi values for kind of timber frame construction. So there are a few around. If not, you have to calculate them based on that junction.
Is it a system where potentially, if an architect was using a manufacturer's product, you could turn and ask the manufacturer to run a thermal bridge calculation to prove that the detail that's being proposed using their product is reasonable? Would they be able
Possibly,
to
yeah.
demonstrate? Would they be able to demonstrate and say, in sometimes, you know, where we turn around and say, could you do me a dew point graph and show me that there is no potential interstitial condensation? And they come up with a very simple thermal graph, and they say, yes, here you go. We've done our review, and no interstitial condensation will occur. Then you could be assured that there isn't going to be a risk. Would, in your opinion, do you know if manufacturers would be in a position to undertake that function to help the industry?
I think if you were looking at, say, a timber frame supplier, and they had, you know, the wall hue values, the roof hue value, they could calculate those psi values. Potentially, it would just depend on the system and the junction, I think.
Okay, a few more questions are coming in. Part L identifies the location of thermal bridge locations and what photos are required. Okay, fine, right, that's an answer to the question. Right, when looking at condensation risk assessments, what do you think of the boundary conditions specified in BS 5250 versus those within the Centre of Window and Cladding Technology, technical note 33? What should be used, i.e. BS 5250 looks at much higher means of monthly temperatures, whereas the Centre for Window and Cladding Technology guidance expects -5 degrees to be used in assessments.
I don't think the temperatures, because it's like a ratio, I don't think they make a huge amount of difference. So I think, but the boundary conditions do vary. I'm not 100% sure, but I think you've just got to be cautious that the ones you're using, for example, if the furniture is going to go up against it, and things like that, you've just got to make sure that you're using something sensible.
So, I mean,
sorry.
obviously, the Centre for Window and Cladding Technology technical note versus the British Standard, which one has weight of prevalence? Which one would you lean towards?
I mean, I would say the Part L uses reference the BR guidance, so I'd probably err on that side. But
is that the Centre for Window Technology Cladding technical note? Is that the British Standard, which is
British
5250?
I'd
Yeah,
probably lean to 5250, but it almost using a little, figuring out what's actually the most sensible for your building.
because I presume one's one of the prescriptive code and one's a guidance note.
Yeah.
As in the Centre of Technology. Okay, that was a very big question, that one. Right, there's one here. Right, probably an answer here. Manufacturers such as H&H and Unilin provide construction details and correspondence PSI values. I think that's probably an answer to a question that I posed. So H&H, I think that's Celcon, isn't it? Celcon blocks is the H&H. Elmhurst Energy have produced a guidance documents for photography, which can be issued to developers. So I think that's information that somebody has passed over about Elmhurst Energy and their issue. So Elmhurst Energy have produced guidance documents for photography, which can be issued to developers. So that may be an aid to offer.
Yep.
Then it comes back to my question above is not clear. It was asking where I can find thermal bridge calculation diagrams that is in the presentation. So yeah, in your presentation,
like the conventions.
Yes,
Yeah,
the conventions that you referred to. Yeah, where could you find it? Is those in the British Standard or?
It is. I can never remember the number off the top of my head, and I don't want to give the wrong one. Let me just find it.
We've got to the end of the question, so
yeah.
Unless anyone else has anything else to add.
So those conventions are in BR 497.
BR 497.
Yeah.
Okay, thank you.
And that's the ones that Part L references.
Okay. Now we got more messages. Oh, very good. Yeah, right. Well, if that's all the questions that we've got. I just want to thank Emma. Thank you so much for giving your time to present to our members. You know, it was a brief introduction. It was a beginner's guide to thermal bridging, and it set out for those who've been in the industry for some time, a bit of a refresher, but it also just focuses the attention on how important it is to ensure that the detailing of coal bridging is undertaken. And now it's very much important that we pick it up on site, and with the onset of photography, photos, and detailed analysis of where we should be looking, there is a clear focus within approved document L that we need to actually ensure that those who do building control need to ensure that they actually pick up these items and not let homes become leaking houses. One item that's come through, which I will raise, is in a 2-story house example, if the thermal bridging was not as good as it should be, but all the thermal elements are meeting the U value requirements, what effect would this have on the SAP and the EPC requirements?
So if you weren't calculating your thermal bridges, you'd use that kind of actual figure of that 0.2, and that would be compared to that 0.05 figure in terms of your calculation. But yeah, in reality, it was that picture of that window. Let me see if I can find it. In reality, what will happen is it will be this sort of scenario. So if you don't think about them, actually your heat loss, actually insulating the wall has sort of, very little effect overall. So it's, you do want to think about it. You'll lead to kind of cold spots. So yeah, discomfort, potentially condensation and things like that, as well as that additional heat loss. So it's definitely something.
So would that actually be reflected in the EPC rating? Because
really,
if it followed all the U values and it designed to the U values and they air tested and they produced the EPC, and the EPC was of a value B, that wouldn't really though show the deficiency in the coal bridging that have occurred.
Yeah, so it's often part of the performance gap there.
So that's probably a negative point of just following what's in part L, that's in U values, and testing it by focusing on one item. It would fail. I think somebody's come back with the answer, which is about it would fail the DER TER. The answer to the question, the U values and TBs, it would fail the DER TER. So would it show up there on the DER TER? If you put in 0.2, it probably would, wouldn't it? It would fail.
I guess the U value, you need your U value to pass.
Yeah.
But if you're not calculating your thermal bridges,
so maybe that's something that maybe that's something that I think building control practitioners should be asking the question about: have you considered the thermal bridging within the U value calculations and within the overall DER TER calculation?
Potentially, I think, particularly for dwellings, it's become, you almost like need to calculate them now, because of that default. The difference between your notional and actual building is so big, so it makes a lot more sense to calculate them. But if say you've got limited time and there's not, you can't calculate them, I would say it's worth still spending time, like optimizing them as much as possible. So even if it's not reflected in your EPC, at least then in reality, your building's a bit better if you've not got the time to do that. At least you can do something.
So ideally, then building control practitioners should be asking questions around thermal bridging within their plan assessment, and equally, architects should be questioning energy consultants like yourself about what around thermal bridging and areas of concern, and making sure that they're well detailed and incorporated within the overall thermal value calculation.
Yeah, because they're becoming just increasingly more of a concern, and as you can see, there's no point just focusing on improving the U values. You've got to look at both, otherwise there's just very little improvement.
Right, and I think that is the absolute take home from this presentation. All of it has been very useful, but I think absolutely it's about asking the right questions of the people who are submitting information, for those who are building control, and for those who are designers, making sure that you are asking the energy consultants to ensure that all the areas of concerns are covered. So with that, I'd like to thank Emma for the presentation and for offering your
Thanks.
slides, which will be handed over to the delegates in this attendance. And for those who have attended, thank you so much for your time. It brings an end to this session. We as a region will have a break, but we're back in September with our conference in Guildford. So please go onto the website, view that, and if you are able to attend, please do so. Other than that, I wish you all a good evening. Thank you.
Brilliant. Thank you. Cheers.
Thank you, Michael.